All right, so we're going to take a look at last type of function for chapter 4. So we did rational functions in parts 1, 2, and 3. Part 4 is radicals. Okay, we don't go into as much depth with them, so we're pretty much going to do everything with radicals today. So we'll do a little bit with graphing and some algebraic solving equations. So first of all, what do radical functions look like? So radical functions are functions that have roots in them. It can be a square root, cube root, but it has to be some type of root. And there's names for the different parts of the expression. So I just want to go through what some of the names are that we're going to use. So first of all, anytime that you write a radical expression, if you see a number that is on the outside of the radical, like this number I just circled in purple, that number is called an index. The index always has to be a number that is bigger than 1, and it can't be a decimal. It has to be an integer. What the index tells you is the type of root that you need to do. Right? So like a 3 on the outside means we're going to be doing a cube root. If it was a 5, we'd be doing a fifth root. If you don't put an index, like in that problem, there is no number on the outside of the root. That means it's a square root. It's like the index is a 2. So whenever you don't see an index, we always assume it's a 2. What you write underneath the radical, so actually I should have mentioned that term too. So this entire thing right here, that is called a radical, or you could also call it radical expression. Either way, radical or radical expression. The part underneath the radical, that's called the radicand. It's the thing that you're taking the root of. So if I wrote something like square root of 9, 9 is the radicand. That's what I'm taking the square root of. The actual symbol that you use, that's just called a radical sum. So the radical sign is the symbol that contains the radicand. So any questions on those different terms? Radical sign, radicand, radical expression, or index? And then if you take a radical expression, like, just look at that part, square root of x minus 2, and then set it equal to something, you've now created a radical equation, because now it has an equal sign. And eventually we'll look at solving some radical equations. That'll be the last thing. I already said that to you. So if you don't see an index on a root, we always assume that it is a 2. Now, when you write something with a radical, there is actually another way you can write it without a radical and have it mean the same thing. There is a power that you could raise x minus 2 to, and it would mean the same as square root. Does anybody know what power means exactly the same thing as a square root symbol? Yep.
1/2.
To the 1/2. Yep. So if you had, let's say you type in on the calculator, once it comes up. Okay, so you type in square root of 48. You get that number. If you wanted to do the square root of 48 and you didn't want to do it with the square root, the radical sign, you could do 48 raised to the 1/2 power. Raising to the 1/2 means square root. What do you think cube root would be if you didn't want to write it with the cube root symbol? we could raise it to the 1/3. Okay, so taking the cube root is the same as raising to the 1/3. Caleb, how about the 5th root?
It would just be 1/5.
It would be what?
1/5.
Yeah, it would be 1/5. It's the same as taking the radicand and raising it to 1 over the index. That's what it is. It's 1 over the index. Now, in that last one, in particular, when you rewrite that, you end up with a power to a power. X to the 4th to the 1/5. Does anyone remember what you do with your exponents when you have a power raised to another power? Yeah?
Don't you multiply?
You multiply them. Yeah. What's 4 times 1/5?
4/5.
4/5. Yeah. So that last one, if you rewrite it, you can simplify it. That's one reason why we might take something that has the radical symbol and rewrite it. So x to the 4/5. Right. Any questions on rewriting something that had a radical symbol into an exponent that's a fraction?
Did you multiply the 4 and 1?
Where, right here?
Yeah.
Yep, I did
Okay.
4 times 1/5. And that's how we got x to the 4/5. All right, so one thing that we might see in the book is the directions, principal root. Okay, like find the principal root. When it asks you to find a principal root, we're going to break it down into 2 cases. Whether you're looking at an even root or an odd root. So we'll start with an odd root. So let's say that I had to try to explain to somebody what a cube root was, and they had never heard of cube root before. So let's say we were trying to figure out the cube root of 64. Right? And they weren't sure how to do that. Well, to figure that out, I would say you're looking for a number that you can multiply by itself 3 times because of that 3 right there. And when you multiply by itself 3 times, it has to come out to 64, like 2 times 2 times 2. No, that doesn't work. So what you're really solving is an equation like that. Can you find a number that you can raise to the 3rd power, and the answer comes out to your radicand? If you can figure out how to solve that equation, then you know the cube root of 64. So in this case, what would be the cube root of 64? 4. Yep. And what if I did something like, let's say you didn't know the cube root of -8. Let's say, all right, think of it like this. What number can you raise to the 3rd power and get an answer of -8? You're solving this equation. What would be the answer in that case? -2. Yep. So notice when you're doing cube roots, you can do the cube root of a positive number, or you can do the cube root of a negative number. There's no problem. And that's true for any odd root. You can take odd roots of positive numbers, negative numbers, zeros, fractions, or decimals. So basically there's no limit. Anything you want. That's odd roots. Any question before we look at even roots? Okay, so even roots are a little bit different. First of all, when we're dealing with an even root, we have to make sure that the radicand is 0 or higher. Just think of a square root. Why does this have to be 0 or higher if you want to take a square root of it? Yeah?
For those negative imaginary.
Right. If it wasn't 0 or higher and you tried to take the square root of it, it would be imaginary. Right? And we're not we're not looking at anything that has to do with imaginaries. Okay, so and that's every even root, square root, fourth root, any even. Okay, I'll always give you a number that's 0 or higher. So that's the first thing. Now, the second thing is if you were trying to find a number that you could raise to the second power and get 25. What number can you raise to the second power and get 25? 5. Or -5. But when they specifically ask you for what's called the principal root, we're only going to want one answer. Which answer do you think we would want? Yeah?
5.
5. Yeah. So when you're solving for a principal root, even though, yes, you do get multiple answers when you do even roots, like square roots, we don't want to write the negative answer. Okay? We are only going to write the positive, or I can't say positive. We're only going to write the answer that is not negative. Because if you took the square root of 0, that would be 0, and it's not positive. All right, so any question on what that means? So principal root basically just means you're giving me one single answer. For odd roots, it's kind of automatic. You'll just get a single answer when you solve it. But even roots, you could get multiple answers, and we don't want the negative one. So not the negative one's wrong, it's just principal means not negative. Don't do the negative. Okay. So let's look at what happens here. See what I did there? Smaller, larger. Wow. Crazy with the fonts.
Right.
All right, so we want to figure out what happens when we take the square root of 4, if it gets smaller or it gets larger. What is the square root of 4? 2. So what happened?
Smaller.
It got smaller. Let's try another one that doesn't come out to a nice number. Let's do the square root of 18. We get 4.24. What happened?
Smaller.
So it got smaller again. Can anybody think of an example where when you take the square root, it stays the same? It doesn't get smaller. Yeah? 1. Yeah. If you take the square root of 1, you get 1. So it looks like when you take a square root, sometimes it gets smaller, or it could stay the same. What about another number you could take the square root of, and it would stay the same? 0. Right. If you take the square root of 0, that is 0. It stays the same. Well, let's try something else. Let's take the square root of 0.5. Square root of 0.5, 0.71 if we round it. What happened that time? Got bigger. So the answer to the question, when you take a square root, does it get smaller or does it get bigger? Well, it depends. Sometimes it can get smaller, sometimes it can get bigger, sometimes it can stay the same. It can do anything. Depends on the number you started with. Any questions on that? And if you're wondering, how can that happen? Well, if you check it, take 0.71 and square it. And you do roughly get back what you started with, 0.5. So it does work. That is correct. It did get bigger. Does anybody have a guess in general when the square root of a number would be bigger than what you started with? Yeah?
One that's between 1 and 0.
Yeah, any square root between 1 and 0 would get bigger. Any square root that's exactly 1 or 0 would stay the same, and then everything else that we didn't mention would get smaller, like 1 and higher. Yeah.
Can it act the same way with negatives?
Well, remember with negatives you'd get imaginaries. Yeah, so we're not going to think about negative with square roots. All right, let's graph a couple even roots. I'm going to show you how you type them in. So we'll start with square root. And I also want to do fourth root. So the way that you do a fourth root, press 4, press math, and then press option 5. That's how you do a fourth root. 4, math, and then option 5. Let's do zoom 6 and take a look at it. So there's your square root. And there's your fourth root. Let's make that bigger. Okay, what do you notice about the fourth root and the square root? You notice anything at all about them? Yeah?
Fourth root is smaller and lower than the square root.
The red one is under the blue one? Always?
No.
Not
No.
always.
Where is it? Where does it look like it's under the red one? It might be easier if I made it
Close to
bigger.
0.
The red one is under the blue one.
After like.
After 1.
After 1. Yeah. After the number 1, the red one is under the blue one. Before 1 and between 1 and 0, the red one is above. And if I zoomed in more, you'd see it better, but it is above. Where do they intersect?
We'd have to check.
We would have to check, but where you would think they intersect from just looking at it, it is where they intersect.
1, 1.
They do intersect at 1, 1. In fact, even if you put in another root, like 6 root, and I graph that one with it, that one still intersects at the point 1, 1 with all the others. Okay? It's a little hard to see because the line is kind of thick right there. But now the 6th root is under all of them when you get past 1. And then before 1, they all switch places. The blue one would be on the bottom, the black one would be in the middle, and the red one, just barely can kind of see it, the red one would be on the top. Anything else you notice about like the direction of these roots? Like looking at the domain, what do you notice? All positives and what else? Yeah?
Infinite?
Okay, so it does go forever to the right, but it includes more than all positive numbers.
Also includes 0.
It also includes 0. So it would be easier to say what it doesn't include. The domain is everything that is not negative. Not negative. For the same reason I said right here, not negative. Okay? You can't use negative numbers when you're dealing with even roots. So these kind of graphs have what I call a starting point, and they curve in one direction. Okay? They do keep going up forever. The blue one, the red one, and the black one. They never level off. Okay? Think about when you take the square root of a number. If I keep putting in a higher and higher number right here, the answer just keeps getting higher and higher. It's not like if I put in a high number, eventually the square root just stops at like 25,000, and then it never goes any higher. Nope, it'll keep going higher and higher. So a couple things about even roots. If you don't shift them, stretch them, or transform them in any way, they all start at the origin, and they all go through the point 1, 1. Now, if you say, what happens if you shift it up? Well, if you shift it up, then it doesn't go through the origin. It goes through a new point. And we will talk about shifting and stretching and reflecting these functions. just like we do with every function we study. Okay, so the domain of these graphs, they all start at 0 and they go to infinity. That's for any even root function that has not been stretched, shifted, or reflected. And the range is the same thing. If you go back and look at all the graphs, the lowest that any of them go is 0. And the highest, well, they're just going to keep going higher and higher as you head further to the right. So there's some general properties of even roots. Now we're going to look at odd roots. That was it. Yeah. All right. So let's look at some odd roots. You can type in odd roots exactly the same way you do even roots. You press the index, math, option 5. But if you already have a root typed in, you can just highlight the index and you can just change it to whatever you want now because it's already typed in. So I'm going to do a cube root and I'm going to do a fifth root. And I just want to look at them and see if there's any difference between how these roots look and how even roots look. Okay. What do you notice is a big difference right away? Yeah? Yeah, sorry, Jim.
It's not just after 0 and positive, it's also going to negative.
Right, it also goes into the negatives. So when we're looking at odd roots, they do not have a starting point. They have a center point, and they curve in each direction. They should be connected, but how come the calculator is having trouble connecting them right there? What's happening in the graph that the calculator always has trouble with? Right, it's getting very steep there. Right? It's almost vertical. So the problem is they can't connect it. Right? What I want to do though is let's zoom into that box, like maybe -3 to 3, so we can see it a little better. And then I'm just going to ask you a few more questions about it. Okay, so again, you can kind of see it's having trouble connecting it, but it should be connected. All right. And how about that graph? Does it look like they have any points all in common?
Maybe 0.
0,
0, 0.
0, 0. Yep, they all go through the point 0, 0. Anything else?
It's like
-1, -1. They both go through that point right there.
and so positive.
They both go through +1, +1. So there are 3 points that they all have in common. Any odd root that you graph will go through those 3 points if you don't stretch it, shift it, or reflect. So that's what we call just the basic function. It's not transformed. And another big difference we picked up on is the domain and the range. This time, the graph goes left and right forever, and it goes up and down forever. That's why when you're doing like a cube root, I told you earlier, you can take the cube root of any number you want. Positives, negatives, or 0. That's because the domain is all real numbers. Okay, so they're both roots, but they do have a very different look. So any questions on the general look of an even root versus an odd root? So we're going to look at transformations next. Just like every function we study, all the transformations for radicals are exactly the same. So I'm going to copy that down so I have a little bit more space, and we'll write we'll write everything down. All right. So when we're talking about radicals, when I refer to inside the function, I mean right there, under the radicand. When I talk about being on the outside, I'm talking about the C and the D. All right, let's start with what A does. A is addition or subtraction, but it is on the inside. Does anybody remember what kind of transformation is addition and subtraction? Is it a shift, is it a stretch, or is it a reflection? It's a shift, yep. And what kind of shift? Yep. That's horizontal. Yep. Now we have to be careful with anything that's horizontal. Plus would move your graph which way? Yep.
To the left.
To the left? Yep, good. And negative would move to the right. Okay, so A is a horizontal shift. How about B? It's still inside the function, but now it's multiplication instead of addition or subtraction.
Stretch.
And what kind of stretch?
Horizontal.
Yep, that's a horizontal stretch. And remember, that is backwards. So for example, if B equaled 3, you would say that it's a horizontal stretch by factor of 1/3. The bigger that you make B, the more compressed the graph gets. That's how it works. If B was 2, then you would say that that's a horizontal stretch. That would be a horizontal stretch by 1/2. Or a factor of 1/2. And the last thing that can happen with B is if it's negative. What happens when we have a negative? The same thing's going to happen on C too. A negative would cause the graph to flip or reflect. We just have to say over which axis. If B is negative, reflect over which axis? Think about it. B is horizontal, so it would be a horizontal reflection, which reflects it over the, yep.
X.
So horizontal reflection would look like this. It's flipping left to right. Yeah, so that would reflect over the y-axis. Okay, so that's A and B. That's everything on the inside. Now we're going to look at the outside. What does C do? That's multiplication, but it's on the outside.
Vertical stretch.
That's going to be a vertical stretch. Okay, I'm not going to write as many examples here because C is not backwards. If C is 3, it stretches 3 times as much. If C is 1/10, it stretches 1/10 as much. Okay, so it's the same. So if C equals 4, that's a vertical stretch by a factor of 4. And one more thing about C, if it's negative, what's a negative with C going to do? Yep.
Flip the whole thing over the x-axis.
Right. That's going to cause, because C is a vertical, it's going to cause a vertical reflection, which means it flips up to down. Right? That's over the x-axis. Okay, so we've described shifting left and right, stretching left and right, reflecting left and right, stretching up and down, stretching up and down, reflecting up and down. The last thing is the D. What is D going to do? Yeah, it's a vertical shift. That causes a vertical shift. And positive would shift the graph which way? Yep, up. And negative is down. Okay, so that describes everything that can happen with the transformations, and it's exactly the same as every function we've looked at. And the reason I use the letters A, B, C, and D is because when you describe the transformations, you have to follow that order. So the order you would list transformations in, assuming you had all 6, you would list your horizontal shift first, horizontal stretch second, horizontal reflection third, vertical stretch would be 4th, vertical reflection would be 5th, vertical shift would be 6th. That's the order you always want to list them. Okay, so just following the A, the B, the C, and then the D. All right. So, as I said before, similar to transformations we've done with other functions we've studied. And let's describe the transformations here. First thing, when you are describing transformations, you never compare a square root to a cube root. They're two different kinds of graphs. So you'd compare a square to a square or a cube root to a cube root. You always have to compare two comparable things. All right, so we're comparing the square root of x to the square root of x minus 2. What would you have to do to this graph to turn it into that graph? Yep.
Horizontal shift right too.
So this would be a shift 2 units to the right. Shift the basic graph 2 units to the right. So that didn't have all 6 transformations, it only had 1. So we only have to list 1. It's not necessary to say, like, don't shift up and down, don't reflect over the x, don't reflect. You don't have to list everything you don't do. Just list what you actually do. All right. How about this one? The square root of x plus 3. What would we do there?
Shift 3 units to the left.
Yep, this would be a shift 3 units. To the left. Okay, any question on that one? All right, let's look at this one. What's wrong with how k of x is written, at least compared to what I gave you on that page? It's okay to have a negative x, but if we want it to match, like, identical to what's there, what would we have to do with this first? Yep.
Parentheses around that to get
No, there's no parentheses in that. But what you have there doesn't match what's there. If you're trying to match things up identically. Yeah?
There's no x value for B.
There's what?
There's no x value for the B. So like for the 3, there's no. Like it says like B of, not of x, but times x on the original.
So how would you make the one that we have look more like that?
Oh, I got no idea.
Yep.
X would need to be the leading coefficient, so it'd be X minus 3.
What you said was partially right.
I don't think I used coefficient right. Or,
You have the right idea. Yep.
You do negative x plus 3.
Right. It should be written as negative x plus 3. If you're trying to match this up to that template, the x should come first. The number without x should come second. So now, how many transformations do we have in this one? Yeah, 2. So we do have to make sure we do them in the right order. What would be the first transformation? Yeah.
Shift 3 units to the left.
Shift 3 units, which way did you say?
Left.
Left. Okay, and then what would be the second transformation?
Reflection over the y-axis.
Reflect over y-axis. Now, if we graph that, is that the kind of graph that has a starting point and it curves in one direction? Or is it the kind of graph that goes in both directions? Yep.
would it be one direction since it's just a square root?
Right, it only goes in one direction. And what direction does a square root normally go in? Normally curves to the, normally it would curve to the right. So this is what a square root would look like. Something like that. What's the first thing that we just said we're doing to that graph?
Shift 3 units left.
You're shifting it 3 units left. So when you shift it 3 units left, it would look like, do this and do that. So shifting it 3 units left would make it look like that. And then what does it say the last thing we do is?
Reflect over the y-axis.
Reflect over the y-axis. So when you reflect this over the y-axis, let's just make another copy of that, and sure, make it purple. What's going to happen when you reflect that green one over the y-axis? Like, where's this point going to end up? Where?
Positive 3.
Positive 3.
Comma 0. Yeah. This point is going to end up over here, and the graph is going to end up curving which way?
To the left.
To the left. So what the final graph is going to look like is that graph in purple. It's been translated 3 units to the left and then reflected. So the point here is when you're drawing a even root function, it can curve in a different direction than the right if you reflect it. Yep. There's actually 4 different ways a square root function can look. It can either curve to the right, to the left, or if you did another reflection, you could curve. You could curve like that, or like that. Those are the 4 directions for square roots. Yeah.
What would happen if you had like a -2 or 3x? How would you reflect that?
I know, like if I had another number here.
Yeah.
Well,
Greater than 1.
that would cause a compression. So
Okay.
I would have to do something like this. If it was, say, let's say you said compressed by a factor of 2, I would
just
have
a negative.
I would have to go like that first, and then
Compress it
flip
and
it.
then flip it.
Yeah. So that would squish it by a factor of 2, and then flip.
So
Yeah.
flipping's the last step.
Yeah, so the flipping would come after the stretching.
Okay. Thank you.
Yep. But that one didn't have any stretching, so. Did all that. Okay, so when we are sketching radical functions, that's the next thing we're going to do. We need to find what I call the original start point or center point. If it's an even root, you're going to have a start point, and it would have started at the origin. But if you transform it, it might not be at the origin anymore, like we did in this picture. I don't know where the picture went. But when I drew the picture with the different colors, it didn't start at the origin anymore. It moved. It started at 3, 0. So we've got to find that new starting root. If you're doing an odd root, odd roots look more like that. We've got to find the new center point. So I'm going to show you how you find the new start or center point when you're doing a sketch. Let's start with the x value. To find the new x value when you are doing a shift, you take the radicand and set it equal to 0. This is the radicand. The a and the b are the only two things that can cause the graph to move left and right. That's it. So a and b are the only two values that would affect this. C and D have nothing to do with the second part of the equation. So you set the radicand equal to 0, solve it. That's your new x value. Now, let's say you get something like this. You'd set this equal to 0, solve it, and write down the answer. That's your new x value. Once you get that x value, you're going to plug it back in. You're going to take whatever you get, you're going to plug it back in right there, and then you're going to do out your arithmetic, and that will calculate the y value. So take what you get for x, plug it back in, do it out, and that's equal to the y value. Now, that'll give you a single coordinate. That's not enough to do a sketch. All you know now after that is my graph starts right there, or my graph has a center point right there. What we need now is a few more points. If you're doing an even root, it's a little easier. Only you've got to check points on one side. Maybe you do 3 more points like that, and you get a nice curve. If you're doing an odd root, then you're going to have to check points on one side and the other side to get the picture in both directions. Okay, so even roots, you're probably going to need about 4 points. Odd roots, you might need about 6 or 7 points. But we're going to use the table on the calculator to get these points. So we're not going to get any of them by hand. Yeah?
When you set the radicand to 0 and you plug it back in, do you plug it back into the original equation?
Yeah, you plug it back into the original problem. Yep. So let's try sketching this cube root. Okay. First, when we sketch it, are we expecting a graph that curves in one direction or both?
Is that a 2 or a 3?
That index, that's an index of 3. Yeah, that's going to curve in both directions. Okay. So keep that in mind. What's the equation that I would write down to find the new x value for my center point? Yeah, Judith?
Set the equation to 0.
And what would you set equal to 0?
So 0 equal, is it flipping in the root, like 3 minus 2x?
The radicand.
Yeah.
3 minus 2x. And what else?
Can I call a friend?
Sure, because right now we don't have an equation. We don't have anything we can solve. We just have 3 minus 2x. Yep.
Equals 0.
Equals 0. Okay. So let's solve for x. So add the 2x. And what would be your last step to get x by itself? Divide by 2. Okay. So that is the new x value of your center point, 1.5. Now we're going to plug 3 halves back in, right here. We're going to do it all out, and that's going to give us the answer for y. So let's fill it in. What's 2 times 3/2? 3. And what's 3 minus 3? 0. What's the cube root of 0? 0. And what's 0 times 2? Still 0. Plus 1. 1. So the number that's going to affect whether it moves up or down is really just this number at the end. So it moved up 1. All right. Now, to graph that, I need a few more points. I need some points that are bigger than 1.5 to the right, and I need some points that are smaller. There's no set values you have to use. Just pick some that are spread out. All right, so let's put in 2 times the cube root.
How did you do that again?
So 2 times 3 for cube root, math, 5. So 2 times the cube root of 3 minus 2x. Make sure you get out of the radicand for the plus 1. Right, let's go to our table. We can check 3/2 comma 1 just to make sure that that was correct. Yep. So that's the center. And let's pick a few values to the right. I would say like 5, 7, and 10. And then pick 3 values to the left. 0, -5, -10. That should be plenty of points to get a good sketch. Okay, so let's graph it. All right, so we've got our center at 1.5, 1. We've got 5, let's see, 5, -2.8. About right there. And then we've got 7, about -3.5. 1, 2, 3.5. And then positive 10, we're at about -4. 1, 2, 3, about right there. Okay, so there's the curve going to the right, and now do the ones to the left. 0, just under 4. -5, we're a little bit below 6. Right around there. And -10, a little above 6.5. 1, 2, 3, 4, 5, 6.5. Looks pretty good. So there's your curve. So just try to draw that best you can. Remember, it does get kind of steep in the middle, so the calculator might not do a good job of making it look connected. But maybe it will. It depends how steep the middle gets. Mine maybe should be a little steeper. Yeah. So overall, we have a pretty good sketch, but maybe it's a little steeper than I drew it in the middle. That's okay. All right. Any question on sketching an odd root? All right. I don't want to go through it, but if we were to sketch it, would this graph have a start point or a center point? Yep.
Start point.
It would have a start point. And if you were to look at the curve very generally, which one of those 4 would it be? So A would be the direction that a normal even root would curve in, but we're doing something here that's going to change that. Let me draw them. Let me fix how I drew these. So we got A, B is fine, C, D. Yeah, that looks better. So it's not going to be A, yeah? It's going to be, you think it's going to be C?
I think so.
I don't know.
I
Oh,
agree.
cool, yeah.
Or D? Yeah, I think it's going to be C. Because what's going to happen is this negative is going to cause a horizontal reflection. So the graph that would normally curve to the right is now going to curve to the left. So it's going to look more like that. So this graph would be, it would look similar to C. The exact details, we'd have to do it all. But any question why it would look like C? Okay, so that's the sketching. And then the last thing we're going to look at is just solving a couple equations. One or two we'll do by hand, and then one I'll show you how to do on the calculator. The important thing with solving a radical equation is you have to make sure the radical is by itself. That's an example of a radical that's by itself. That's an example of a radical that is not by itself. You've got two together on the same side. You have to have a radical alone on one side. Like that. Once you get a radical alone, you're going to raise each side to the power of the index. That means if you're doing a square root, you're going to raise each side to the power of 2. That's going to cancel the square root. If you're doing a cube root, you would raise each side to the power of 3 to cancel the cube root. And that's what we're going to do in this one. Okay, when you finish solving it, always double check your answer and make sure that it does work. All right, so in this one, it's perfect. We already have the radical by itself. If you had something like this, then no, you do not have the radical by itself. You'd have to minus that 7 to the other side first. But we don't have that. So we're going to cancel that cube root by raising each side to the third power. Yep. So raise this to the third. Raise that to the third. When you cube and cube root, they cancel each other out. What's going to remain on the left-hand side?
X squared minus 2x plus 2.
Yep. X squared minus 2x plus 2. And what are we going to end up with on the right side?
X cubed.
X cubed. Okay. Based on the highest exponent, what kind of equation is that? Yep. Cubic. And what do we try to get a cubic equal to when we're solving? Yep, get it equal to 0. So I like to make sure the highest term is always positive. So let's put everything on the right. So we're going to have x cubed. And what's going to come after that if we put everything on the right side?
Minus 2x.
Before that.
No, plus 2x. Oh. Plus x.
Let's put it in descending order.
Yeah, plus x squared.
Minus x squared.
Oh my god.
Yeah.
Get me out of here, I swear to God.
So we got to minus that. And then
Plus 2x.
Then we have a plus 2x. And lastly, minus 2. Okay, so now we've got everything on one side. Whenever we have 4 terms, unless something works out nice, that's going to be hard to solve. So something is going to work out nice here. And we can use a special kind of factoring. Does anybody remember the name of that factoring when you have 4 terms?
Is it by grouping?
By grouping. Yep, exactly. So you're going to factor out what you can from the first 2, and then from the second 2, and hope you end up with 2 things that look the same. If we don't, then for this one, we would be kind of stuck. What can you factor out of the first two?
X squared.
X squared. And if you factor out x squared, what would that leave you with? X minus 1. Perfect. What can you factor out of the second two terms? Or the last two terms?
2.
2. If you factor out a 2, what are you left with? X minus 1 again. So this is going to work. Okay? If that didn't happen where we got the x minus 1 twice, that would have been an issue. Okay, so now look at this and look at that. What do both of those have in common? X minus 1. So now we're going to take out that entire x minus 1 from both. If you take it out of the first one, what's left? Just the x squared. And what if you take the x minus 1 out of the second one? Plus 2. So now we've got two factors equal to 0. What do we do with each factor? Set them equal to 0. So take the first factor, set it equal to 0, and the second factor. What do you get when you solve the first factor?
1.
1. What's going to happen when you try to solve the second equation? You're going to get an imaginary because you'd be trying to take the square root of negative 2. If something comes out imaginary, we're done with it. We're going to ignore it. So from this part, there's no solution. So the only answer that we got was 1. And what do we have to do with the 1?
Check the pitch radius.
Yeah, just check and make sure it works. Let's plug it in. All right, so the original problem looked just like that. Let's plug in 1. What's 1 squared? 1 minus, what's 2 times 1? 2 plus 2. And then what number are we filling in for x? 1. What's 1 minus 2 plus 2? 1. What's the cube root of 1? 1. And does 1 equal 1? Yeah, so then it works fine. So that is correct. So that's a cube root problem. Any question on that? Let's try a square root problem, but let's change that a little bit. Let's do equals 7. Okay. Do we have a root that's already by itself? Yeah. So what side would you raise, or what power would you raise each side to? Yep, square. Square each side. Dylan, what do you get on the left when you square that? What do you get on the left? Yeah. So you're squaring the square root of something. What happens when you square and square root the same thing? No, you can. You can square. It's like adding 5 and then minusing 5. No, the left side's not going to come out to 0. What's going to happen? Nico, what's going to happen on the left side? It's going to come out to, just say it one more time?
Square 6x plus 12. Or wait, no, just 6x plus 12.
Just 6x plus 12. Right? When you square something and square root it, it cancels out. So 6x plus 12. And what's the right side going to come out to? Yep, 49. And now we just have to finish solving. So minus your 12. 6x will equal how much? 37. Yep. And last step, divide by 6. And there's your answer. X equals 37 over 6. And if you plug it back in and check it, it works fine. Just trust me. All right. So any question on solving that kind of equation? All right. So the last one. The last one we're not going to do algebraically. We're just going to type it in y1 and y2 and look for where the graph on the left is above or equal to the graph on the right. All right. What feature do we have to use a lot when we type something in y1 and y2? On the calculator, there's a certain feature we use a lot. Well, when you're graphing something in y1 and y2.
Like today? What?
Well, I don't think we've used it today, no, but we've used it a lot. Yeah. So it's not a button. It's something the calculator does for you. It figures out for you. The intercept, yeah. This is going to involve finding an intersect. So we're going to put in the 5th root of 9 minus x squared and x squared plus 1.
Mr. Hager,
Yeah.
which option do you press when you do the math thing?
Option 5.
Okay.
Okay, so we got to just look at it carefully. The 5th root was the graph that I did in blue, and x squared plus 1 is the graph line red. Is the blue graph ever above the red graph?
Yeah.
Yes, there is a section. Where is the blue one above the red one? You don't have to give me like exact, you can just kind of describe where on the screen.
Just like x is 0, like on the y on itself. Trevor, can you help me on this, bro?
What is it?
It's like
So
a-
where is the blue one above the red one? Just
In the middle.
in the middle, yeah.
All right.
It's not over on the left, it's not over on the right. It's, I'd say right in the middle. Okay, that's what we have to figure out. How are we going to figure out? Now I want it more specific than the middle. Yeah?
The intersect.
Right, we have to find the intersect. And this time you can equal the graph. Right? So when we find the intersect, what kind of symbols are we going to use on our interval? Because the two graphs can be equal to each other. What two symbols, when we write our interval, are we going to use?
The regular air closed brackets.
Brackets, yes. You're not using parentheses. If you put parentheses, that means you don't have the equal to symbol. We do have the equal to. So you've got to use brackets. So calculate the intersect. If you just do it randomly, you'll get one of them. So I got the higher end, 0.73. And now when I do it the second time, I got to be a little bit more careful.
Just graph it over them actually, so don't worry.
It's probably 0.73, but we can't, or negative 0.73. But don't always assume it's symmetrical. Just find it. So negative 0.73. That is the x values that if you plug them in, you will get the blue graph above the red graph. If you pick anything outside of those numbers and you plug it into each, then the red will be above the blue. And that's not what we want. We want blue above red. Well, any question on that one? Yep.
Would that just be the answer? You
Yeah,
want us-
that's the interval from negative 0.73 to 0.72. If they said to write it in inequality notation, you could do this. It's the same thing. depends how it asks for the answer. But it's between those two numbers, including the numbers themselves. Okay, any other question on that? All right, so that's everything that we're going to be doing on radicals. Okay, so most of the questions are just individual ones, 20 to 22. That's the only range that you have in the homework. So I think it's about 10 questions. So we'll look at that tomorrow. And since we finished up everything, there's nothing we have to finish tomorrow in class. We'll do the review, and then on Friday we will have our test.